Let's start with velocity versus time graph. Now this is kind of messed up. This drawing. I don't know what happened to this. I guess the formatting of all this Microsoft did not work out well. Um, I'm going to need a ruler to correct this, and then once we correct it, we can actually make it look a little bit better. Um, this should actually come down like further out like this, right? This should be a straight line. And notice the spacing here from 1 to 2 is like this big, but 0 to 1 is really not that big. So I'm going to try to correct this. This is the way it should be, like this. And this should be, um, this should be 0 right here, okay? As well as this should be 0 as well, right here, right? And the time axis should be going from here across like so, okay? This should be the time axis. Not this, okay? And this graph should go from, it should be like that, okay? So, whoa, how did that two lines happen there? That's kind of weird. It should be like this, okay? So this should not be here like this. And this should not be here. And this should not be here as well. So it should look something like this, okay? And here's your 1, here's your 2, 3, and so on, okay? And this should not be here right here either. This time axis should be moved down to here. Okay, so if you were to think about how we went from position versus time to velocity versus time, we used the slope of position versus time to draw the velocity versus time graph. Well, similarly, if we were to take the slope of the velocity versus time graph, okay, the velocity versus time graph gives you, the slope of that will give you the acceleration, okay? Now, if it is between the two time intervals, then it is average acceleration. If it's at instantaneous time, at any time t, then it will be the instantaneous acceleration, okay? But for now, the slope, whether it's average or instantaneous, the slope of the velocity versus time graph will give you acceleration, okay? Um, Again, if this delta t is the two time intervals, so you're finding the slope of the secant line, but if you are finding the slope of the tangent line, that is just the derivative of your velocity function with respect to time. Okay, so for those of you who are already taking calculus or already took calculus, that's what it should be. Okay, let's take a look at the unit for acceleration. Okay, unit for acceleration is delta v is basically meters per second. Okay, delta v has a unit of meters per second, and delta t has unit of seconds. So if you were to look at this, I know somebody's going to say, yo, Mr. Kim, shouldn't the seconds cancel out and give you minutes or meters? And the answer is no, because this meters per second divide by second is same thing as saying, right, meters per second times the reciprocal of that second. Therefore, it is meters per second squared is what meters per second is. Okay, so this is the unit for acceleration. Okay, so unit for acceleration is meters per second squared, or the length dimension divided by time dimension squared. Doesn't always have to be meters and seconds. All right, so to find the slope of the velocity versus time graph, let's take a look at where the slope of the velocity between 0 to 1 second. So if I were to find the acceleration from 0 to 1 second, so that's the average acceleration, right? By definition, average acceleration is delta V over delta T, right? And since I am looking for average acceleration from 0 to 1 second, my delta V is V final, which is 1 second, minus V initial, which is V at 0 seconds. Divide that by T at 1 second minus T at 0 seconds. That is, here my velocity at 1 second happens to be 1 meter per second. So 1, right, meter per second, minus T at V at 0 seconds is just 0 meters per second. Divide that by T1, which is 1 second, minus 0 seconds. Therefore, I get 1 meter per second over 1 second, and that is 1 meters per second squared. I guess if you want to put x hat, you can do that, okay? Because it is technically a vector. Now let's take a look at the average acceleration from 1 to 2 seconds. So I guess I could put this vector symbols up there as well. So the acceleration between 1 to 2 seconds is equal to, okay, here my V2 seconds minus at V at 1 second divided by T2 minus T1. Therefore, velocity at 2 seconds happens to be right here at 2 meters per second minus velocity at 1 second happens to be 1 meter per second. Right? Divide that by 2 seconds minus 1 second. Therefore, I have, again, 1 meter per second over 1 second. Therefore, 1 meters per second squared, etc. Now let's take a look at acceleration from 2 to 3 seconds. Okay. So for this, I'm looking at V at 3 seconds minus V at 2 seconds divided by T at 3 seconds minus T at 2 seconds. So this one, V at 3 seconds is 2 meters per second minus V at 2 seconds is also 2 meters per second. Divide that by 3 seconds minus 2 seconds. That comes out to 0 over 1, therefore 0 meters per second squared. So there's no acceleration happening between 2 to 3 seconds because the slope is 0. Does that mean it wasn't moving? Well, my velocity is positive 2 meters per second between 2 to 3 seconds. So it is definitely moving at 2 meters per second. at constant velocity. Therefore, there's no acceleration. But it is moving in the positive direction at 2 meters per second. All right. So what about from 3 to 4 seconds? So my acceleration between 3 to 4 seconds is velocity at 4 seconds minus velocity at 3 seconds. Divide that by t at 4 seconds minus t at 3 seconds. That is, velocity at 4 seconds is 0. Okay? So 0 meters per second minus velocity at 3 seconds is 2 meters per second. Divide that by 4 seconds minus 3 seconds. So therefore, this becomes negative 2 meters per second divided by 1 second, or negative 2 meters per second squared x hat. Well, what does that mean? Well, you're going, first of all, in a positive x direction, because notice how my velocity is a positive value. From 3 seconds to 4 seconds, it starts at 2 meters per second and is actually slowing down, going in the positive direction to 0 meters per second at 4 seconds. So it's going slowing down, slowing down, slowing down, going in the positive direction, and then it stops at 4. So here, the rate of slowing down is 2 meters per second squared in the negative direction. All right? So this is still moving in a positive direction, right? Slowing down, okay? Okay. All right. Any questions? Okay, good. Then let's move on to the next page. Now let's take a look at the same graph, which is kind of messed up again. I don't know why this is not fixed. This has to be fixed. Let me redraw this again. Here we go. I'm going to redraw this. Like that. And then this would be the right. This would be our 0 right here, and this is also our 0. And then our time axis would be this. This is our time axis, okay? And of course, this is my 4, 3, 2, 1. And this would actually go from here to here, like so. Okay? So, I mean, this doesn't exist. And this doesn't exist. All right? That's what it should look like. So, what happens? Well, when we look at the velocity versus time graph, right, the area of the picture, so the area of this velocity versus time graph, now the area has to be between your velocity graph and your time axis. Your time axis has to be the border for either the velocity being positive or negative, right? So when you look for the area, you look for the area between the time axis and your velocity graph. So since my velocity graph is positive in this case, we will be finding the area between the time axis and the velocity graph like so for area like that, okay? This area, right? So the area between the time axis and the velocity graph represents delta x, okay? So how does that work out? Well, we know by mathematical definition, the average velocity is equal to delta x over delta t. If we multiply delta t to both sides, right, this is what we get. Well, if you look at it, this v represents the height, delta t represents the base, okay? So if I were to take a look at, let's say we're moving 2 meters per second, constant rate, for 1 second. So 2 meters per second times 1 second should give you 2 meters. Well, here's the graphical representation of that. Here, I am moving at 2 meters per second, constant velocity for 1 second. So the area here should represent that delta x. Well, let's see if that's true. So here is the area, okay? So let's take a look at from 2 to 3 seconds, okay? My v is equal to 2 meters per second constantly, right? My t is equal to 1 second. Therefore, my delta x should be, right, 2 meters per second times 1 second should be 2 meters. Okay? Well, let's take a look graphically. Here's my base, and here's my height. The area of this rectangle, right, so this area of a rectangle is equal to, well, according to here, it's height times base, right? So height times base. Well, the height happens to be 2 meters per second. That's the height. And the base happens to be delta t, which is 3 minus 2 seconds, which is 1. Therefore, this becomes 2 meters per second times 1 second, and it does exactly come out to be 2 meters. Okay, so the area is same as delta x. It proves it right there. So even if we're not going at a constant velocity, we could be moving at an accelerated velocity, the area will still represent the delta x. Okay? So here, from 0 to 1 second, we know that delta x is equal to the area of that triangle right here, right? Which is equal to 1/2 base times height, right? And since base is delta t, right? This is delta t for the base. And the height is v, right? So 1/2 times delta t is 1 minus 0 times v, which is 1 meters per second, right? Second. Therefore, I get 1/2 times 1 minus 0 seconds is 1 times 1, I get 1/2 meters exit. And it is positive half a meter. Okay, that is my delta x from 0 to 1 seconds. Okay, I should write down 0 to 1 here. Well, what's going on for my 1 to 2 seconds? Well, my delta x from 1 to 2 seconds, I need to find the area of this triangle right here, right? I need to find this area of this triangle. And then I need to find the area of this rectangle right here. So I need to add these two areas together to get my delta x. So I need to find the area of this plus the area of that, right? Which is, right? This area here is 1/2 times base times height plus, classroom light just went off again. Times base times height of this, right? So for this one, I get 1/2 times, the base is 2 minus 1. The height is also 2 minus 1, right? Because the height is from here to here. Base is from 2 minus 1. Height is 2 minus 1, right? Plus base again here for the rectangle, which is 2 minus 1, times the height, 1 minus 0. Okay? So if you work this thing out, you're going to get this becomes just 1. This becomes 1/2 times 1 times 1 is 1/2. So you get 1.5 meters x hat. And that is the delta x between 1 to 2 seconds. I hope that was okay for everybody. Okay. We already did this, right? 2 to 3. So I'm just going to write it down. So delta x from 2 to 3, right, seconds, is equal to, right, base times height, which is, right, base is 3 minus 2, height is 2 minus 0, and we get 2 meters x hat. So we already got that done. Now for h, it says 0 to 3 seconds, from here to here, right? So what is the displacement for 0 to 3 seconds? Well, delta x from 0 to 3 seconds is equal to, right? Simply, it's just the total area, right, from 0 to 3 seconds. Therefore, all I have to do is just add them up. I add 0.5, right, plus 1.5 plus 2. This plus this plus this. And what do I get? I get positive, positive, positive. So positive 4 meters x hat for the total displacement. Well, what about if I do I? Well, what about if we just do delta x from 3 to 4 seconds? Well, that's easy too, right? Because again, this here is area that we're looking for, right? That area is again base times height, and half of that, because it's a triangle, and that is 1/2 times base, which is 4 minus 3 seconds, times the height, 2 minus 0 meters per second. Right? Therefore, 1/2 times 1 second times 2 meters per second. And I get positive 1 meters per second x hat for 3 to 4 seconds. All right. Any questions so far? All right. So let's take a look at the next page. All right. Well, the next page states, all right, well, what if we have an instantaneous velocity, right? Instantaneous velocity. Well, instantaneous velocity is simply, instead of looking for the slope of a secant line, right, we will look for the slope of a tangent line, right? Just like what we did for homework problem, okay? So I'm not going to go like too crazy into this, especially since this is not quite calculus based, okay? So if we were to look at position versus time function, okay? For those of you who are already taking calculus, you probably know this already. So the position versus time function, right? Looking at this, let's say, okay, if I were to use this as an example, okay? So if I were to say, okay, 0.5 t to the 4th power, right, plus 10 t squared plus 3, and I think this was negative in front, right? This is going to be a really weird position function. It's going to be like quartic, not quadratic, but quartic, like 4th power, right? So if I take a derivative of this, the first derivative of my position function, which is dx of t dt, right? That actually represents my velocity function. And that is equal to, right, 4 times negative 0.5 is negative 2 t cubed, right, plus 20t plus 0. Okay? So, if I plug in my time t, at any time, I could plug in 1 second. If I plug in 1 second, what do I get? I get negative 2, right, plus 20, so I get 18 meters per second. Okay? So at t is equal to 1 second, right, my v of 1 happens to be negative 2 times 1 cubed plus 20 times 1, right? So my instantaneous velocity at 1 second comes out to 1 cubed is 1 times negative 2, I get negative 2 times my plus 20, I get 18 meters per second at 1 second. But what happens at 2 seconds, right? So at t is equal to 2 seconds, all we have to do is just plug in that 2 seconds into this function right here, right? So that velocity of 2 seconds is negative 2 times 2 cubed plus 20 times 2. This is 8, right? 8 times 2 is negative 16 plus 40, and I get 24 meters per second. Okay? You could even calculate exactly what time it's going to stop. So I could just put in 0 for my velocity here and solve for time, and I should be able to calculate exact time when this thing's going to stop. Instantaneously, of course. All right? So that's how the instantaneous velocity works. So instead of finding a slope of a secant line between 2 time frames, instantaneous velocity takes a derivative of this position function and find the slope of a tangent line at any time t. So once I find the derivative, that function can represent the slope of the tangent line when I plug that time in at that time. All right, so whatever the value I get is the velocity value, instantaneous velocity value. And that instantaneous velocity can be positive or it can also be negative. All right. All right. So here, okay. This instantaneous velocity at any time t is the slope of the line tangent to the curve of the position function at that time t. All right, and that's the example that I gave up there. Okay, so you're not quite responsible for it, but it's a nice idea to have, especially if you're taking calculus. This will help tremendously if you understand this. Okay, so if I were to give another example where x of t, this is position as a function of time, that's like 2t squared plus 4t minus 3, right? If I want to find instantaneous velocity at any time, first thing I do is I take a derivative of this. The first derivative of my position function, right, which is same as dx of t dt, is my velocity function, and that is 4t plus 4, right? So to find, right, let's say what happens when t is equal to, let me make a different color, t is equal to 0, right? T is equal to 1, and then let's say t is equal to 2 seconds, right? So let's find out what happens to the instantaneous velocities at all these different times. So v of 0 is equal to 4 times 0 plus 4, and at 0 seconds, my instantaneous velocity is 4 meters per second, xl. Okay? And at 1 second, my velocity at 1 second, instantaneous velocity, is 4 times 1 plus 4, which is 8 meters per second, xl. And at 2 seconds, my velocity at 2 seconds is equal to, right, 4 times 2 plus 4, which is 8 plus 4, right, is 12 meters per second, etc., etc. Okay? So you could keep going. You don't even have to be having a full, whole number here. You could have like half a second here, or 1.745 seconds here, right? And here you could have like a pi seconds. It doesn't really matter. It doesn't have to be a whole number. Okay? So what happens if you find instantaneous acceleration now? Well, instantaneous acceleration is pretty much the same thing, okay? Where instead of taking a derivative, taking a secant line between the two velocities at two different times, the instantaneous acceleration is, right, just the derivative, the first derivative of the velocity function, right, which is dv of t dt, right? Or it is the second derivative of the position function, okay, which is d squared x of t dt squared. All right. So if we were to use the previous problem right here, let's say this one, if I take a derivative of this, it's only going to be just 4. So this motion will have constant acceleration of 4 meters per second squared all the time. All right. However, if I take a derivative of this, I would have negative 6t squared plus 20 as my acceleration. So it's going to be a different acceleration. It'd be, a matter of fact, very snappy, snappy motion, because derivative of acceleration is jerk, and derivative of jerk is snap, right? And then crackle, pop, and so on, right? So here, let's take a look at example, if a particle moving at velocity in the x direction given by this velocity function. So our velocity function happens to be, right, v of t happens to be 3t, right? Well, if I want to find the average acceleration, my average acceleration is delta v over delta t, right? So if I want to find the acceleration between 6 to 12 seconds, the average acceleration for that is just v at 12 minus v at 6 seconds divided by t at 12 minus t at 6 seconds. And that is, if I plug in v at 12 seconds, this will be 12 times 3, right? Minus, right, 6 seconds, 3 times 6. Divide that by 12 minus 6. And that is equal to, right, here I got 36 minus 18. Divide that by 6. That is 18 over 6, which is 3 meters per second squared. That's the average acceleration. Well, does that change? Well, we could actually take a derivative of this. Since we know acceleration is equal to dv of t dt, right? If we take a derivative of this function, I get 3 meters per second squared. So it is a constant acceleration of 3. It doesn't depend on time at all. No matter what time it is, it's always going to be 3 meters per second squared all the time, right? It's a constant, right? This is a constant acceleration, okay, at any time. So no matter what time it is, it's always going to be 3 meters per second squared. All right? Any questions? All right. So let's take a look at the next page. And I had to show them how to do this slightly so that people were not panicking. I'm going to see if I can help you guys start this thing out. Now notice where the 0 is for my velocity. So I think it's important that we draw our time axis here. Let me see if I can find. OMG. I'm such a nerd. I had a ruler in my backpack. So here, I'm going to actually draw my time axis, right, straight across the 0. This is important to have that time axis. Okay, this is time in seconds. Okay. Now, since this is a velocity graph, this velocity is very important that you read this versus this, right? So the slope of velocity versus time graph will give you acceleration values, right? The slope. And if you take a look at the velocity graph, and if you look at the area of this, will give you the position or the change in position. Okay? So for the acceleration graph, I will also place my time axis right here. I hate when my ruler slides over like that. I'll draw a straight line. Here's my time axis. And notice this is not labeled. I should try to find the greatest slope value and then scale it out so that I have enough room. So let's work these slope values out. Okay, let's take a look at the slope value. So the acceleration from 0 to 1 second, what would that be? That would be A at 1, I'm sorry, V at 1, V at 1 minus V0 over T1 minus T0. And that is 10 minus 0, whole thing over 1 minus 0. So what do I get? My acceleration comes out to positive 10 meters per second squared from 0 to 1. Now let's take a look at acceleration from 1 to 2. And that is my velocity at 2 minus the velocity at 1 divided by T2 minus T1. Therefore, the acceleration comes out to, here looks like 15 minus 10 over 2 minus 1. That looks like positive 5 meters per second squared. So that's the acceleration from 1 to 2. Similarly, if I were to look for the acceleration between 2 to 3 seconds, and that is, right, V3 minus V2 over T3 minus T2, and that looks like 0 at V3 minus 15 over 3 minus 2. So this one looks like negative 15 meters per second squared. And last but not least, this one, the acceleration from 3 to 4 seconds, right, is equal to V4 minus V3 over T4 minus T3, right? Therefore, V4 is negative 20. V3 is minus 0 over 4 minus 3. So this one looks like negative 20 meters per second squared. So I'm going to make 5 increments of 5 for each one. So if this is 0, this is positive 5, 10, 15, 20. Negative 5, negative 10, negative 15, negative 20. Then, if you look at from 0 to 1 second, my slope value is 10. So, I couldn't see the lines. So 10 is the slope value. So my acceleration from 0 to 1 second is that. And then from 1 to 2 seconds, my acceleration is positive 5. All right? And then, when I look at from 2 to 3 seconds, my acceleration is negative 15. Now I know you can actually put you could put one of these Johns to make it look like a real function. Open circle, close circle. That's fine. Okay. And 3 to 4 seconds is negative 20 meters per second squared. So that way over here, and that would be like so. That would be the acceleration versus time function from looking at this, which is the velocity versus time graph. All right. Now let's take a look at what's going on for position versus time. Now we're going to assume, right? Assume the particle starts at origin, which means the x initial is 0. Okay. You have to be careful with this. Sometimes they let you start at positive 10 meters or maybe even negative 5 meters. So you got to find out. If they don't tell you anything where to start, you could always assume it starts at 0. So you could start at 0 right here. And now to find the area of this right here, okay, represents my delta x1. My delta x 0 to 1 is 1/2 base, which is 1, times height, which is 10. So my delta x from 0 to 1 is equal to positive 5 meters. So I start at here, and I'm going to go 5 meters. Now, I didn't scale this out yet, so I can make this like, I don't know, 5, 10, 15, 20. I probably could go like 5, 10, 15, 20, like that, So I'm going to say 0 meters, 5 meters, 10, 15, 20. So each two lines are worth 5 meters. So I'm going to go from here to here, 0 to 5, okay? And I'm accelerating, so I'm sort of like going, and not in a straight line, but it's sort of curved, like almost a parabola. Well, actually, it is a parabola, okay? Then I have to find this area here, right? This area plus this area here to add them together to get my displacement for 1 to 2 seconds. Okay? So how do I do that? Well, to find the area of this, it's just 10 times 1. So this is 10 meters. This area here is 15 minus 10 is 5. Half of that is 2.5 times 1 is 2.5. So this total area here, so x1 to 2, is equal to 12.5 meters. Can everybody see that? And it's positive 12.5. Okay? So from here, from 5, I'm going to go 12.5. So that's 5, 10, 12.5. So it's going to go like that. Because total of this plus this should be 17.5, and boom, it's 17.5. All right? Now, if I look at x 2 to 3, I have to find this area here, right? And that is 1/2 times base is 1 here, 3 minus 2, times the height, which is 15. And I am still going in the positive direction because my velocity is still positive, even though I'm slowing down going in the positive direction. So my area here is still a positive value. So this comes out to 7.5 meters, and it's positive 7.5. All right? So here, it slows down to 0 at 3 seconds. I'm going to have to slow down to stop. So my slope value at the top is going to be horizontal at 3 seconds. All right? So this is 5, and 7.5 is like right here. And it's going to actually slow down to like this. So that here at 3 seconds, it's going to be horizontal tangent line. And then here, this is, now I'm going in the negative direction because my velocity is negative. Therefore, the area for this, right, here is delta x 3 to 4 is, the base is still 1 because it's 3 to 4. Height, however, is negative 20. And then you have to do half of that because it's a triangle. So half of 1 times negative 20 gives me negative 10 meters exit. That means I am going in the negative direction of 10 meters. So here's 5, right? Starts here, 25, I guess, and then 5, 10. So I end up here at 15 meters. So that's what it's going to look like for the position versus time graph. So what happens when I add up all the area? Well, when I add up this area here, 5 plus 12.5, right, plus 7.5, and I get 25, minus 10, and I should end up at 15. boom, 15, like that. So my total displacement of the total trip is positive 15 meters, right? And if I were to look for the total distance traveled, now it's a different story. 5, right? And then here, 17.5, right? And then 7.5 is 25, plus 10 is 35 meters, is the total distance. But total displacement is positive 15 meters x hat. All right. Any questions? All right. I would like you to try this, page 30 for homework. Okay. And I will end my today's lecture there. All right. Any questions? All right then.